All right, hello everyone. My name is Lannon-Paakspuu. I'm currently a master's student here at UBCO, and I work with Dr. Lovegrove and his lab. Welcome to your ENGR437 lab on hydrogen fuel cells and hydrogen gas production. I understand this course is about railway systems engineering, but as it has a focus on clean energy transportation and the relatively new hydrogen fuel cell passenger train, I hope some of you will find this interesting as it relates to fueling fuel cell vehicles and equipment as a whole. So I'll first be introducing fuel cells and providing some basic working principles behind them. After that, I'll be going over several common methods that are used to produce hydrogen. I'll be talking briefly about both renewable and non-renewable production methods, and then quickly relating all of this to using this fuel on board a hydrogen-powered vehicle. Now, the lab assignment will require some research on your part, as I will be providing basic introductory information to you in this video, and I hope this will allow you to do further research on your own and answer your lab questions successfully. Now, here's some things about fuel cells that you may or may not already know about. I'll be talking more specifically about hydrogen fuel cells today, as they are most commonly used, and that is what I'm familiar with as well. So hydrogen fuel cells convert hydrogen gas into electricity using oxygen from the air. That electricity can then be used to power motors or auxiliary devices, which of course are both used in any vehicle today. There's many different types of fuel cells available and in development as well. Most commonly mentioned, I guess you'll see, are proton exchange membranes, alkaline fuel cells, molten carbonate, solid oxides, and then you can also get microbial or organic fuel cells. There's tons, and there's many more in development as well. Now, each different type of fuel cell has their own benefit, their own downfalls. They're made out of different materials, and they all perform slightly different. Now, if you didn't know, fuel cells were first used in space, and they were used because we had the technology available, and it was too expensive to be available to consumers. But if you're going to space, I guess you don't care how much money you're spending. And they were used in space because they're safe. They emit very low levels of heat, especially if you're going to compare it to a gasoline vehicle or a diesel vehicle. The fuel is extremely lightweight for the energy that's contained in it. Again, you wouldn't want to bring diesel or gas up there as a heavy liquid. And not only that, but when you create electricity from a fuel cell, it produces water. And the water can then be used to fuel the astronauts. So it's a major benefit for using fuel cells in space. Again, to relate to this course, fuel cells are used in the Karadia Island passenger train to provide power to those electric motors. And fuel cells produce zero harmful emissions at use. Now, if you look more upstream about, if we're going to talk about life cycle analyses, then you look upstream from where your fuel cell comes from, and also where your hydrogen fuel comes from. It might not always be made in an emissions-free process. So it's good to be thinking about upstream processes and where total life cycle emissions come from, and we'll talk a bit about that moving forward. All right, now I'll give you a basic intro to fuel cells, or hydrogen fuel cells more specifically. They all operate under similar principles, and this might seem a little bit confusing because I'm kind of going over how two different fuel cells work, but this will at least provide an introductory level of comprehension into how fuel cells work. So hydrogen and oxygen come into the fuel cell as the two parts of the fuel. Now, hydrogen gas is the tricky part because you have to produce that somewhere. Oxygen I have in parentheses there because we just pull it from air. If we're on Earth in the atmosphere, then it's pretty much free for us because there's 21% of air is oxygen. And for most cases, at least for transportation uses, we don't need a higher oxygen percentage than that 21%. Now, in the fuel cell, otherwise, hydrogen gas molecules are going to be broken apart into hydrogen ions, which are positively charged. If that happens, it happens at the anode, and 2 electrons are released there, which pass through a circuit and into an external load to power whatever that load is, be it a light bulb or an electric motor. Electrons then pass to the cathode. In another type of fuel cell, oxygen gas molecules, so O2, might break apart at the cathode into double negatively charged oxygen ions. And they would be doing that using the electrons there. Now, somewhere in the fuel cell, water molecules are then made using hydrogen and oxygen. And remember that this reaction is exothermic, meaning that the reaction produces heat. This heat must be managed as to not damage your fuel cell or anything else nearby. And this is similar to any power producing technology, but typically you get less heat from a fuel cell than you would, at least compared to an internal combustion engine. Now, I have two figures shown on the right here. They're both different types of fuel cells. The one above is a solid oxide fuel cell, and the image below is a proton exchange membrane fuel cell. You can see that they basically look the same and they do kind of work the same, but the solid oxide fuel cell creates water at the anode by passing oxygen ions through the electrolyte. They're moving to the left. Whereas the proton exchange membrane fuel cell passes hydrogen ions through the electrolyte, moving right there to make water at the cathode. I've shown you the chemical reactions that happen on the right as well. So the solid oxide fuel cell above, you can see the oxygen ions pass through the electrolyte there. Now, shown here is a simple animation of what happens in a fuel cell. I just really like this GIF because it gives you a better idea. More specifically, this is a proton exchange membrane fuel cell. Hydrogen gas as H2 is fed from the tank. At the catalyst or the anode, the hydrogen gas breaks apart into two hydrogen ions, releasing two electrons. The hydrogen ions are then able to pass through the proton exchange membrane, where they meet up at the cathode, the other catalyst, and use oxygen from the air to finally mix back together with the electrons and leave water from the exhaust. Now the electrons are shown here powering a light bulb, but anything that needs power can be attached here. So why fuel cells? And why do people believe that they're a potential replacement of, at least in part, some internal combustion engines moving forward to a greener future? Now, petroleum use and emissions are lower in fuel cell vehicles than for gasoline-powered internal combustion engine vehicles. The only product from a fuel cell vehicle tailpipe is water vapor. But even with the upstream processes of producing hydrogen from natural gas or petroleum products, as well as delivering and storing the hydrogen for use in fuel cell vehicles, the total greenhouse gas emissions are cut in half, and petroleum is reduced by over 90% compared to today's gasoline vehicles. We also need to start depending less on fossil fuels, specifically petroleum products, as they are non-renewable resources and cause a massive amount of difficult social and political issues and conflicts around the world. Fuel cells do not need conventional fuels such as oil or gas and can therefore reduce economic dependence on oil-producing countries, creating greater energy security for the user nation. Now, fuel cells would also allow us to prevent harmful pollution from being emitted in population-dense areas. Today, there are massive costs to society in terms of health impacts from internal combustion engines being driven near people. By driving fuel cell vehicles, on the other hand, and even with the hydrogen being produced from fossil fuels, we remove the area where pollution is created from densely populated areas and can manage the pollution in more remote areas. Now, fuel cells have a higher efficiency than diesel or gas engines as well. So we talk a lot about efficiency everywhere nowadays, and it's important as an engineer to know why efficiency is important. In buildings, if you're a civil engineer, and engines, if you're a mechanical engineer, and how your computers work, if you're an electrical engineer, or any system as an electrical engineer. So yeah, fuel cells have a higher efficiency. It's really important to know that. Most fuel cells operate silently, and especially compared to internal combustion engine vehicles, and they are therefore ideally suited for use within buildings such as hospitals, and can help noise pollution in general. Now, the maintenance of fuel cells is relatively simple since there are few moving parts in the system. Obviously, right now, if you took a fuel cell vehicle into a mechanic, they probably would have no idea what to do with it. But the change is relatively simple. You can now see, electric vehicles haven't been on the road for too long, and they certainly haven't been as widely driven as they have been as widely popular as they have been in the last 5 years. But there's more and more people who are getting comfortable with working with the electrical components of electric vehicles. So I would expect the same trend to occur with fuel cell vehicles. So just go over some major hydrogen fuel cell developments that have been happening around the world. If you guys have been following clean transportation development over the last 2 years, there have been many large developments and announcements made related to fuel cell vehicles and the general hydrogen economy, as it has been coined. Here are some of the ones that I've been following over the last year or so. The first one comes out of Germany, and it's one that I'm sure you're all aware of, since you'll be using, I believe, at least the same train design for your project in this course. After over 10 years of field testing and design refinements by Alstom, the Kradia Island Hydrail passenger train was put into regional service in southern Germany in 2018. It is a hydrogen fuel cell battery hybrid and was a featured centerpiece of the 2019 International Hydrail Conference. Now, the project has had such success over the last year and a bit that another 60 trains have been ordered for service over the next 5 years. Alstom also intends to demonstrate the island in North America in spring 2021. This passenger train was designed with the intention to match the performance of the Coradia Lint, which is a similar, like almost the exact same train, but it's a diesel electric model, while eliminating local emissions by depending on hydrogen as a fuel. And I'm not just talking about pollutant emissions, I'm talking about noise as well. Now, the island has a power output of 400 kilowatt, a range between 600 and 1,000 kilometers, and can carry up to 300 passengers. At a very similar unit cost to the Lint, the island offers an opportunity to replace existing Lint trains, which are used all over the world, including the O train in Ottawa, for example. Replacement costs can arguably be recovered through lower maintenance costs. Then here at the University of British Columbia Okanagan campus, led by Dr. Gordon Lovegrove, the Okanagan Valley Electric Regional Passenger Rail, or OVR-PR, is being designed as a regional passenger hydrail train connecting small and rural communities over a 300-kilometer stretch between the U.S. border and Kamloops. Now, today, large vehicle producers are now beginning to offer fuel cell vehicles available for purchase. Toyota, Honda, and Hyundai all currently have fuel cell vehicles available for purchase. And when you purchase these vehicles, which are a bit pricey, but that's to be expected of new tech, you get a multitude of benefits. I believe each company offers up to $15,000 worth of free fuel at a bare minimum. And then there's potential government rebates, as well as I think I think Toyota and Hyundai have the better benefits if you buy one. Now, to support these vehicles, these companies and green thinking governments alike have started to support the development of fueling stations. Obviously, people need to fuel their cars up. Vancouver, in fact, already has 3 hydrogen gas stations in the city, and there are over a dozen already in the San Francisco area, with more being installed across California. Germany, again, made a massive move towards supporting the growth of the hydrogen economy this year by announcing their national hydrogen strategy. Germany is planning on becoming a world leader in hydrogen production, specifically clean hydrogen production, as well as quickly developing fueling infrastructure for vehicles and supporting hydrogen-related education, research, and development. Now in Canada, Ballard Fuel Cells, which is a local company operating their headquarters out of Burnaby, has become a world leader in fuel cell technology. Hopefully their work will continue to move fuel cells around the world and further support the development of them here in Canada as well. Now, if you're not convinced yet that hydrogen fuel cells are any sort of solution to the climate issues we face today, or if you really like your gas or electric vehicles, perhaps I convince you with something a little more concrete, which is just good old cash. Shown here are stock prices for Ballard Power Systems and Plug Power. Both are prominent fuel cell technology producers. You can see that when the COVID-19 pandemic first hit, these stocks were affected with the rest of the market. but have both since boomed in price as several global announcements have been made supporting the hydrogen and fuel cell industries. Now, I know that stock market prices do not really mean much for how successful this technology might be in the coming years, but certainly this points to the fact that fuel cell technology is gaining traction fast at the moment. Now, hydrogen gas in a gaseous form does not exist naturally on Earth, as it bonds with other elements so easily. However, we can produce it using a multitude of different methods. I have listed some of these methods here, but even more ways are being researched and developed every day. Electricity can be used in an electrolyzer, which is a piece of equipment that uses electricity to split water molecules into hydrogen and oxygen. This is the same process that happens in a fuel cell, but in reverse. Electrolysis can be powered by renewable energy, making it an emissions-free method. The great part about electrolysis is that anyone with power can do it. I tend to think of electrolysis much like charging a battery, in which you take electricity and you convert it into another form to be then converted back to usable electricity later. It's much like a battery in a vehicle where you turn your electricity from your home or your vehicle charger into a chemical energy in your battery, and then it's later converted back into electricity for use in your vehicle. We can also use fossil fuels to produce hydrogen. The production methods vary on the type of fuel used, but essentially they boil down to burning or cooking the fuel in such a way as to extract the hydrogen from the original fuel's compounds. Biomass, which is organic material, typically plant waste, can also be cooked under pressure to extract hydrogen. This is a very renewable method as you're using a renewable resource, but it does pollute quite heavily, at least during the production phase. We'll go into that more later. Now, these first three categories of hydrogen production are fairly well established and currently used to produce hydrogen all over the world, at least in some scale. This last category of production, however, is still fairly new and in development. I've named the three subtypes of water splitting, and I'll go into more detail in the following slides. But these methods use different ways to split water molecules into oxygen and hydrogen. An electrolyzer, like electrolysis, actually does water splitting as well, but it uses electricity. These three methods of water splitting here don't use electricity. They use other sources to split water molecules. Now, with so many ways to produce hydrogen using a variety of inputs, basically anyone, anywhere can produce hydrogen, depending on the sources that are local or easiest to obtain to you. You can see how having hydrogen as the fuel of the future could solve a multitude of political, economical, and social issues that have been occurring over the last 2 centuries since the discovery of oil wells. It boils down to basically everybody having their own energy security and not having to rely on other people for energy. Now, today, about 95% of hydrogen around the world is produced using fossil fuels. The remaining 5% or so is produced mostly through electrolysis with some biomass gasification. Unfortunately, while using electricity in electrolysis may be generally better than fossil fuel options, it's more than likely that the electricity used in this production comes from fossil fuel sources. Now, the pie chart on the left shows the current state of hydrogen production today, as I just explained. And the trend graph on the right shows an expected trend from a 2008 study, which I've chosen to show today as it shows, in my opinion, a more realistic scenario where we continue to rely on fossil fuels for part of our hydrogen demands, but increase our renewables production. If the trend shown on the right is to be closely achieved, clearly we need research, development, education, and investment into these cleaner methods to support their development and achieve this trend. Now, to the graph on the right again, you may be asking yourself right now why production would be increasing so dramatically over a 30-year period. I was assumed in the 2008 study that I pulled it from that sometime between 2010 and 2020, hydrogen and fuel cells would begin to be used in the transport industry, dramatically increasing limited demand from only small specialized industries into the massive industry of transportation. With the major developments I have talked about so far, it seems that this may be the exact situation we are in today. Next, I'll be providing you with some insight into different methods to produce hydrogen. It's important to note before moving on to the next slide that when production costs are shown, these are the costs that the producer of the hydrogen takes on. And they're based on life cycle cost analysis as well as historical data gathering. As the most developed hydrogen production method, steam reforming is one of the least expensive and most commonly used methods around the world to produce hydrogen. Average production rates are around $2 per kilogram of hydrogen produced. The US produces 95% of their hydrogen from steam reforming, and globally, 48% of hydrogen is made from steam reforming. Steam reforming uses natural gas mixed with steam and heat to generate carbon monoxide and hydrogen. The carbon monoxide is then mixed with water in a catalytic water-gas shift reaction to create more hydrogen and CO2. The hydrogen gas is then purified for use. Most commonly, methane is the natural gas used, and the reaction in a steam methane reformer shown on the right here. However, other gases such as propane, ethanol, and biogas can be used as well, which provides an opportunity to source feedstock from different vendors who provide the greatest advantages that the procurer wishes. In fact, basically any hydrocarbon, including oil and gas, can be used as well in this process, but this is less common than natural gas, as natural gas is usually widely available and relatively inexpensive. As this is a fossil fuel dependent production method, there are clear and significant greenhouse gas and other pollutant emissions from this method. The emissions can be partially negated by incorporating a carbon capture and storage system into the production plant. Steam reforming can be used at a wide scale of production from very small plants up to extremely large plants that produce over 500,000 kilograms of hydrogen per day. The image on the right is a photo of a very large-scale air-liquide hydrogen plant. Now, coal gasification requires heating up coal, not really combusting it, to produce hydrogen. As it has been used for a long time to produce hydrogen, it is also a very well-developed and established method that is widely used today. With an inexpensive feedstock and using well-developed technology, it is typically the cheapest way to produce hydrogen. During coal gasification, coal is partially oxidized with steam and oxygen by reacting at high temperature and pressure in a gasifier. Byproducts in this production method are carbon monoxide, CO2, steam, and hydrogen. The carbon monoxide again can then be passed through a water-gas shift reaction, the same as happens in the steam reforming, to remove the carbon monoxide and capture more hydrogen from the steam. Hydrogen must then be taken out of the final mix to purify it for use. Coal gasification is the most polluting hydrogen production method. Due to its high associated level of pollutant emissions, coal gasification is not a highly desirable option without carbon capture and storage. However, its current use in hydrogen production and with a global dependency on coal, specifically in the US, warrants this method's mention here. Costs associated with this method are extremely low, and an abundance of coal means that for large-scale hydrogen production, coal gasification is an option. Now, as carbon capture and storage technology improves and becomes less expensive, coal gasification is expected to be increasingly depended on for hydrogen production, as it is inexpensive and coal is so widely available around the world. Coal gasification can be done at basically any scale, but mostly medium to very large plants. A simple graphic depicting the reactions and inputs to coal gasification are shown here. Now, electrolysis uses electricity to split water molecules into hydrogen and oxygen in a piece of equipment called an electrolyzer. It's a well-established and well-known hydrogen production method, constituting the most effective technique for water splitting, which if you didn't know, as I mentioned earlier, there are many ways to split water molecules. Much like with the emissions-free concept of electric vehicles, the process of electrolysis is emissions-free at production or emissions-free at use in the case of electric vehicles. But it is not completely emissions-free if the electricity used in electrolysis comes from non-renewable sources. Always remember that you have to look upstream in the life cycle of products to understand the true environmental impact of them. The major benefit of electrolysis is the ability to produce hydrogen in small scale applications. Electrolyzers are used for electrolysis and can be fairly compact and modular, allowing for significant variance in the scale of potential applications. I would say that there are two types of electrolysis, renewable and non-renewable. Renewable electrolysis would use electricity solely from a renewable technology, such as solar, hydro, wind, or ocean power. I have italicized nuclear here, as nuclear energy remains under debate by many as to if it is renewable or not. There should be a question in the assignment that addresses this issue. And then non-renewable electrolysis is the second type, which likely just uses grid electricity, but will use, at least in part, some electricity from non-renewable sources such as fossil fuels. Now, using electricity from the current grid, which likely relies on non-renewable sources in part, means that this production method does not completely eliminate greenhouse gas emissions and other pollutants. However, there is potential for the development of renewable power production technologies such as wind and solar to be installed at fueling stations with electrolyzers. This would guarantee a completely emissions-free hydrogen production method. However, current costs associated with this renewable method can be extremely high and vary significantly depending on the type of technology used, the location of the technology, and a multitude of other issues. The table at the bottom here shows some typical price ranges for various types of electrolysis on a per kilogram of hydrogen basis. I'll state again that electrolysis pricing varies tremendously depending on how and where it is done, especially for renewable electrolysis. Another interesting point about electrolysis is that the electricity used in the process can be from mixed sources, of course. This makes the use of low capacity factor renewables, such as wind and solar, that do not produce electricity all the time, to be paired with a steady source of electricity, such as the grid or hydropower. Now, this hybridization saves on costs and allows for some more freedom in plant design and operation, while increasing system capacity factors for those low capacity factor renewables. This is a little complicated. I'm sure not all of you would be familiar with it, so don't worry if you didn't understand that. We can also use surplus energy from large-scale renewables to create hydrogen from electrolysis, therefore storing energy in the form of hydrogen for use at a later time. This surplus energy would otherwise be wasted, but instead would be used to create completely clean and inexpensive hydrogen. On the right here is a diagram of what happens in an electrolyzer. You may have already noticed that it looks quite similar to the fuel cell diagram shown earlier. This is because what happens in an electrolysis, works like a fuel cell in reverse, which you can see electricity is the in and hydrogen and oxygen are the out. Another interesting point that I have down here is a general rule for electrolysis is that it typically takes anywhere between 50 and 55 kilowatt hours of electricity and 9 liters or kilograms of water to produce 1 kilogram of hydrogen. We expect the electricity demand to go down as electrolysis technology improves, but unfortunately, 9 liters of water per kilogram of hydrogen will remain. Next, I want to go over thermochemical water splitting processes, which use extremely high temperature heat, anywhere between 500 degrees and 2000 degrees Celsius, to drive a series of chemical reactions that produce hydrogen. The chemicals used in the process are reused within each cycle, creating a closed loop that consumes only water and produces hydrogen and oxygen. This is a long-term technology pathway with potentially low or no greenhouse gas emissions. As it's in its early stages, no large plants currently exist today that use this method. However, it is expected that this method will be put into large-scale application within the next 20 years. Researchers of thermochemical water splitting have posited that the heat could come from concentrated solar power or from the waste heat of nuclear power reactions. Heat from nuclear power plants is obvious, but shown on top to the right here, concentrated solar power is shown first using heliostats on the left and second using dish mirrors on the right there. These are actually methods that are used to produce electricity as well as heated water, at least in the case of concentrated solar dishes today, and for electricity for heliostats. So these are similar to solar electricity production methods, but instead of producing heat for electricity generation, the heat is directly used to produce hydrogen. Below this are two proposed methods that would use heat to produce hydrogen. This is what would happen in the STCH reactor shown above. The concentrated sunlight in this graphic could be replaced with nuclear weight heat. You can see on this lower diagram that the process is closed loop, with the only products entering the system being water um, and electricity over in this case, and then the only outputs being oxygen and H2. I've shown the chemical reactions here too, but I'm sure this is all a little complicated. In more detail, this shows two examples of water splitting cycles. On the left, a two-step direct thermochemical cycle based on oxidation and reduction of cerium oxide particles. And on the right, a multi-step hybrid thermochemical cycle based on copper chloride thermochemistry, which includes an electrolysis step that needs some electricity input. More introduction information can be found at the Office of Energy Efficiency and Renewable Energies website, which is energy.gov. As this technology is still in its youth, there's no concrete historical pricing data available for hydrogen production costs for either technology. However, life cycle cost estimations have been done by many researchers, and these price ranges shown here are relatively well established and agreed on. Challenges remain, however, in the research, development, and demonstration of commercially viable thermochemical cycles and reactors, such as first, the efficiency and durability of reactant materials for thermochemical cycling, which need to be improved. Second, we need efficient and robust reactor designs that are compatible with such high temperatures and heat cycling. And third, for solar thermochemical systems, the cost of concentrating mirror systems needs to be reduced. Either way, exciting progress continues in this field, which is leveraging synergies with concentrated solar power technologies and with emerging solar fuel production technologies. Biomass, a renewable organic resource, which includes agriculture crop residues such as corn stover or wheat straw, forest residues, special crops grown specifically for energy use such as switchgrass or willow trees, organic municipal solid waste, and animal waste. This renewable resource can be used to produce hydrogen along with other byproducts through gasification. This is a moderately well-established production method and works similarly to coal gasification, except it uses an organic feedstock. Now, biomass gasification is the process of exposing organic material to hot steam and controlled amounts of air and or oxygen under high pressures and temperatures. The process offers a unique benefit in which waste materials and other organic materials, which otherwise might end up in landfills, can be used as feedstock. This method is extremely sustainable as it produces hydrogen using a naturally grown renewable resource and can remove waste from other industries. When biomass is heated to temperatures typically over 700 degrees Celsius without combustion, the byproducts are carbon dioxide, carbon monoxide, and hydrogen, and many others actually, but those are the main ones. This method does emit significant levels of greenhouse gases and other pollutants. However, there is arguably a carbon offset here due to the fact that the plant material absorbed CO2 while it was alive. Now, this point is currently a highly debated topic, with some researchers arguing that there are negative carbon emissions when considering the life cycle CO2 absorption of the plant material used in gasification, and then other researchers arguing for the consideration of solely production emissions from gasification. However you feel about it, greenhouse gases can be removed at the production stage using carbon capture and storage for sure. Now, biomass gasification is expensive at small scale, but is cost effective for medium to large scale plants. The major downfall to biomass gasification are that sourcing biomass at a reasonable cost over long periods of time can be difficult. The cost of biomass varies greatly season to season, and for many other reasons. and therefore the costs of producing hydrogen using this method are volatile. Now, on the right here are simplified example reactions that would occur in the gasification chamber, and then the subsequent water gas shift reaction that you've seen already. Now, C6H12O6 is glucose, which is present in a lot of organic material. In an actual biomass gasification process, there are many, many different chemical compounds that make up biomass, and each has their own quantity of carbon, hydrogen, and oxygen, and therefore create their own reaction products. Now, some are worse and some are not as bad for the environment as others, uh, but it's something good to note. Like if you go look at biomass feedstocks and gasification, you'll notice that some of them give off almost twice as much hydrogen than other ones. Now, also shown here is a very simplified diagram of biomass gasification. Uh, there are many different types of biomass gasification, all of which operate under relatively similar operating principles. So this table here is from a paper that I wrote recently summarizing the estimated production costs and emissions of 4 studied pollutants of various hydrogen production methods. Now you can see here average production cost. That's based on life cycle cost analysis and off of published literature. I've taken roughly 10 or more sources for each method, which are labeled here. And you can see what the acronym stands for down here. To determine an average production cost. I've also determined the emissions in weight of pollutant per kilogram of hydrogen produced for 4 impact categories here. These last 3 rows, you don't need to worry about that for this laboratory, but the external cost of pollutants is basically the cost to society based on the damage that these pollutants do. Now, once you have your hydrogen produced, the next step seems relatively simple. Just getting the product or the fuel to the customer and into their vehicles. But at the moment, there isn't the infrastructure in place yet for transporting hydrogen or for fueling many of these vehicles, at least not at a massive scale. Now, for the Caradia Island, the passenger train that you have to study in this course, fueling infrastructure would likely be custom built or easily transportable. But for personal vehicles, this is not the story. A major barrier to hydrogen development is the requirement to massively change the fueling infrastructure that is currently in place today. Going from liquid fuel at atmospheric pressure to gaseous fuel potentially under intense pressures up to 350 or 700 megapascals, it's a massive change. However, the issue is not as bad as it seems. I would relate this part of infrastructure changes to like how Tesla Motors encouraged charging around North America. To allow their customers to travel far quickly, Tesla installed thousands of strategically placed supercharging stations across North America, allowing for widespread travel in their vehicles. With this kind of strategic introduction of hydrogen fueling stations into the North American market and into the global market, we might be able to more intelligently get hydrogen vehicles onto the road. Now, another point about hydrogen fuel is that 1 kilogram of hydrogen has about the same energy in it as 1 gallon of diesel or gasoline. So this is typically how hydrogen prices are compared to diesel and gas, which is convenient since a gallon of gas is very common price, at least in the States, and easy conversion if you're looking at liters at the rest of the world. And you got to remember here that fuel cells run more efficiently than internal combustion engines. So, with much lighter fuel, and the fuel runs more efficiently in an engine, you get a lot more bang for your buck when you use it in your hydrogen fuel cell vehicle. I also want to make another point here that hydrogen is already cost competitive with diesel and gas. Maybe it's not the most environmentally friendly because I'm talking about hydrogen from coal or from natural gas or petroleum products, which are the least expensive, but it's already competitive in terms of cost. Now, as renewable hydrogen gets cheaper and gas and diesel get more costly, renewable hydrogen will be much more competitive in terms of cost. Now, another interesting part about introducing hydrogen on a global scale, and fuel cells as well, is the social response to hydrogen. People tend to resist change, and in many people's minds, it's still related to the Hindenburg disaster. You have to remember that the Hindenburg held hydrogen in a loose bubble, and when it exploded, when it started leaking, it was easily ignited. But technology today, especially storage technology, is very safe, and they have safeguards in place to prevent ignition and to allow the gas to leak away from the vehicle. So today, I mean, fuel cell and hydrogen technology is just as safe as diesel and gas. So speaking of storage, here are some well-established ways to store hydrogen. Uh, by far, the most common way to store any gas, including hydrogen, is in compressed gas cylinders. And vehicles today use, one or multiple cylindrical tanks to store their fuel. However, these tanks are very heavy, they're very bulky. I mean, to store only a few kilograms of hydrogen under intense pressure, you might have a 100-pound, 200-pound tank. So material-based storage methods, which are still being researched and developed, have shown, at least in the prototyping and lab stages, that they can store as much hydrogen gas as would be in a gas cylinder, but at a tenth of the pressure and half of the volume. And that's for the same weight of hydrogen. Like, let that soak in. A tenth of the pressure and a half of the volume. So material-based and like specifically adsorbents and chemical hydrogen, they're going to really advance the way that fuel cells fit into vehicles and allow users to travel further distances in these types of vehicles. There's actually a company in Vancouver, again, called Hydrogen in Motion, who's doing this